my video that I'm recording, I kind of running low on disk space, so I'm hoping this happened Wednesday. Even though I cleared up some space, it says my disk was full. I'm not sure what's going on, but I'm worried about the video because my 210R class, my video file got corrupted. So hopefully the first half of the lecture file was okay. So what I want to do now, we talked about that circuit with the two inductors, the inductor and the capacitor in parallel. And so I want to show you a demo that Tyler made for us, which is on YouTube. I guess it's a check. You guys can all hear me, right?
Yep.
Okay, good. I don't want to be talking and then nothing's happening. So, all right. So let me show you this video.
The demo before you is meant to demonstrate phase relationship. In this circuit, if you follow this wire, we have the high side going into an ammeter, going to the top of an inductance substitution box, and into a capacitance substitution box. Each line here comes out into a ammeter for each, and then the bottom and grounds are connected. So the ammeter on the left shows you the current through the capacitance leg. The one in the middle shows the current through the inductance leg. And the one on the right shows the total current. We have a AC source here set to approximately 1750 Hertz. And this just shows you how can you have 4 milliamps of current in total current, and each leg shows 30.4 or 30.5 milliamps of current. You have to think about the phase relationship and think about how inductors have resistance themselves, generating this small amount of current. As I adjust the frequency, and therefore the phase, you'll be able to note how the current changes for each leg. And if I adjust the frequency up, you can note the current change in each leg again.
Notice the difference. Oops. The difference in the current through the inductor and through the capacitor was equal to the other current. Okay. Do you guys have questions on that?
Actually, yeah. So, when it's at the resonant frequency, in an ideal circuit, would the total current be 0 then?
You mean an RLC circuit or?
Yeah. Well, in a circuit that Tyler has set up, is that an LC circuit with no R?
Yeah, but the meter has resistance. That's why you couldn't get it down to 0. So in the ideal case, it would be 0.
Okay, so that's why it's like 4 point whatever.
Yeah.
Is due to the small resistance. Okay.
And it was hard. It was hard to choose combinations so that the current through the inductor and the capacitor are way larger. You know, because if you can use the 10 amp scale to do this, then that thing would read 0. You know what I mean?
Oh yeah.
Yeah, we were on the milliamp scale to do this, but if we were able to set this up so we were on the amp scale, probably what happened was that third multimeter would read 0, which would make it more convincing. Although but then you'd forget about the internal resistance of the ammeter. So yeah, that's a good question. Okay. So I want to mention one more problem. I want to skip this one in your notes, but I want to talk about one that's related to the homework. And it's the following. Suppose I have a power supply with a capacitor here, a resistor, and an inductor. And I want to know a little bit about this circuit. I want to see if I can draw the phasor diagram for this. This is actually one of your homework problems. So this is more difficult because of the fact that you have a series parallel combination. But let's go through this carefully. Now, number one, you know that the current through the capacitor is going to be the same as the sum of the currents through the resistor and the inductor, right? That we know. So let me draw a nice big diagram. And I want to draw, since the current through here is the sum of these two currents, I want to draw the current through the capacitor. Hold on, I need to fix this. Hold on a second.
So you make your 0 degree be the capacitor voltage?
Yeah, and the reason why I'm doing that is because if I want to find, well, everything's measured with respect to the total current, right? The phase angle between your total current through the power supply and the voltage across the power supply, the phase angle is measured between those two vectors, right? And so it's going to be easy for me to draw it this way. Now, the parallel circuit, I kind of had a little bit of flipped. That's because the voltage across the power supply and the current through the power supply were right next to each other. This one's complicated, so I think the best thing to do is write what I sub C is here. So let's write I sub C. And I sub C is the sum of these two. How about V sub C? How do I write V sub C? Well, V sub C is going to be 90 degrees to this. Like V sub C will be, I'll draw it. I'll use purple just for the capacitor. It's going to point straight down. Now, what about these two? The voltage across each one of these is the same, right? We know that V sub L has to be equal to V sub R.
But they're 90 degrees out of phase, right?
The currents are, right?
Oh, but the voltages aren't. Okay.
The voltages aren't, right? Because they're in parallel to each other. The voltages are going to be the same, but the currents are going to be 90 degrees to each other. In fact, the current and the voltage are going to be in phase here, but 90 degrees out of phase with this one. So maybe what I can do is draw my current for the, let me use blue for the resistor. And by the way, the sum of these two currents, which are perpendicular to each other, have to add up to this, right? I got to draw a right triangle somehow. like that. Okay, so these two add up to this. This is the hypotenuse. And this has got to be a right triangle because you know that these are going to be 90 degrees apart. The voltage across the resistor is going to be parallel to this. So maybe I need more colors. I don't want to draw it in blue, I guess. The voltage across the resistor.
Just do a dotted line.
A dotted line? Okay, that's a good idea. So that's V sub R. Okay. And V sub R is going to be equal to V sub L. So this is also V sub L. So I'm going to write a comma, V sub L. And V sub C points straight down. So I'm going to take this guy and put it straight down here. I'm going to exaggerate it because I ran out of space here. So this is V sub C. So this vector plus this vector gives me the power supply voltage. Okay, so now I have everything. So the phase angle between the power supply voltage and your total current, we'll call phi. Okay. Now when I draw it this way, the projection of this guy along the x-axis represents basically voltage due to resistance. There's a better term to use than that. Okay. And then the projection of this along the x-axis represents the voltage due to the reactive part of my circuit. Does that make sense? Because remember the drawing I showed you way back. At the beginning of the lecture today, I said that in the LRC circuit, that the X component, the one that's parallel to the current, represents the voltage due to the resistance, and then the one perpendicular to it represents the voltage due to the reactance. And so that's the case here, as long as I define everything relative to the axis defined by the current, the total current. So one of the things I can find out, for example, is the X and Y components of this. The X component is due to the resistance. The Y component is due to the reactance. Okay. In other words, tangent of phi is equal to the reactive part over the resistive part. If I were representing my voltage as terms of complex exponentials, this would be the imaginary part, this would be the real part of my function.
Hey, Professor.
Yeah.
How did you determine that V sub C was down?
Because there's a 90-degree phase shift between I sub C and V sub C. The voltage lags the current by 90 degrees.
Okay. And then everything else can be based off of that.
Yeah. So if I know, for example, let's say something about this guy and this guy, I can figure out this angle called beta. See, if you look at this, the angle beta is related by the following. Basically what I'm doing is setting up that homework problem. And since they both have the same voltage across them, then you can say tangent of beta is R over X of L. So if you know those, then you can figure out this angle. And then this y component is just going to be this minus this. So v sub m sine of phi is going to be this guy minus, where'd it go? This guy. Sorry, this guy. Which is...
Wasn't that v sub r cosine or
Yeah.
sine of beta, right?
And then the other component v sub m cosine phi is going to be...
Is
is that?
sine beta not cosine, sorry. Isn't it, right?
Yes, sorry. And v sub m cosine of phi is going to be what? It's going to be the same thing as the x component of this. And so then you can actually relate the x components to the y components, because in the problem it asks you for what value of the capacitor is the, forget if I have it, the x component over the y component equal to a factor of 10. And everything can be determined by the phasor diagram. I might have it backwards. It might be the y component over the x component is equal to a factor of 10. I can't remember exactly. Okay, so once you have this picture, you can figure out everything. So this guy so this guy is just v sub m sine of phi, and then this is v sub m cosine of phi. Are we okay with that? Questions?
So on the homework, it asks to find the frequency in which the current through the resistor is 0. So then you would set IR to 0 basically, and then have IC equal IL, right?
For this particular question, or is it this
Yeah.
question or the other one?
Isn't this number 18 on the homework? The last problem, whatever. I'm pretty sure this is what it is, isn't it? A parallel. Oh, actually, no, it's not exactly the same.
Okay.
Because in that question, a capacitor is connected in parallel to an inductor. Okay. I was just trying to find the problem in which you were talking about.
Oh, okay. Because I created this problem over the summer, and I added it to the assignment. And I forget. I have to look at the assignment. I forget what number it was. But I added this one just so you get practice with something that's some combination. This would be kind of a long to ask on an exam, but it's a good one to look at. Just how much information the phasor diagram gives you. Now the thing is that there's actually a better way to do this. When you write everything in complex exponentials, it's more efficient. More algebraic, but it's more efficient. And that if you take circuits, I don't know if you guys are taking circuits next semester, you'll probably deal with this next semester. Okay? So I just wanted to set this one up so you can actually do the homework and you can watch the video. All right, so the last item I have is just a real simple question regarding the LRC circuit. I want to say a couple more things about the simple LRC circuit, and maybe things will come a little bit more together. And it's based on the example you see in the slide. So So suppose I have this circuit, and I'm not going to go through and calculate everything just because of time, but I want to say some things about the circuit. And I'm going to draw it this way. I'm going to draw it this way on purpose. Okay, this is going to be 250 ohms. Because the answers to my questions are going to differ depending on how I rearrange these, okay? Oops.
So when they say RLC, does that mean like resistor then inductor then capacitor, or is that just?
Just a name.
So I guess you need to define how they're located in this to find an actual value for each thing.
Yeah, you actually, and it's when you're looking at the voltages between like two of them. That's important. The order is important.
It depends where the resistor is, right?
Yes. And then, you want to look at your phasor diagram. I'm just going to draw the triangle. Okay, so one immediately can calculate a whole bunch of things if we know the frequency. Actually, we know the angular frequency in this case. So we're given omega is 377. So X sub L is going to be 377 hertz times 0.6 henries. X sub C is going to be 1 over 377 hertz times 3.5 times 10 to the minus 6. And then Z is going to be R squared. And then it's going to be this minus this. So let me see if I have these values written down. I do not. So I'll just write the equations in. And then I can find I if V is 150 volts, then I is just going to be 150 over this monster. Okay. And then V sub R, to find V sub R, I'm going to take this thing times the resistance. To find V sub L, I'm going to take this thing times this guy. And to find V sub C, I will take this guy again. And of course I can find the phase angle, right? It's going to be X sub L minus X sub C over R. So I can get a lot of information out of this, and I'm not going to focus on the small v's because I just don't have time right now. The question I want to ask is, the pertinent question is this. What is the voltage drop between this point and this point? But what, not, and I got to be careful when I say that. What is V sub, what is the maximum voltage between those 2 points?
Well, wouldn't that just be equal to the voltage minus VL sub L? Is that what you're trying to get us to find? I don't know.
Is it the voltage minus V sub L? Right, I mean, if you draw your...
All the voltages add up to be V sub M, right? V sub R plus V sub L plus V sub C equals V sub N.
Well, the sum of the... No, what happens is V sub M is the square root of V sub R squared plus V sub L minus V sub C squared.
Oh, okay.
Right?
So it's not actually linear then.
No, it's not. That's the point I was trying to get at, right? Because they follow this triangle. All right. In fact, if you draw your phasor diagram and you just draw, let's say you draw V sub R, and then you draw V sub C, the sum of the voltages across them is going to be, well, I got to draw a right triangle. This square plus that square doesn't take the square root. You see that? So if I want to find the voltage between this point and this point, the potential difference, the maximum value, right? I got to take the difference, or I got to find the hypotenuse of the right triangle formed by V sub C and V sub R. They're 90 degrees apart. They're 90 degrees out of phase. Same thing as if I did these two. If I wanted to find the voltage drop between these two, then I would draw my V sub L up here, and then this would be the voltage drop across the resistor and the inductor. Now that's a point students miss, and I purposely put problems in the homework assignment where you have to actually deal with this. Okay? Now, what if I did the following? Let's say I reverse these two. And I wanted to find the voltage between, or the voltage across the inductor and the capacitor. Then what? What do I do in that case? Well, they're 180 degrees apart, so it's the difference between the two. You will find that when you do the lab and you measure these voltages, that these voltages will be higher than the power supply voltage. Right? Because, I mean, think about it. The voltage across here is LdI dt. And we did problems where, in chapter 32, where LdI dt produced a voltage bigger than the power supply voltage. So expect the same thing here. Energy is still going to be conserved. Are we okay with that? Questions? Okay. So I have in your PowerPoint notes, an extra problem you can play around with. It doesn't show the original problem. I think I have that graph. Let me hold on a second. What happened? I have a problem with the real inductor in your notes, and so you can take a look at that example for more practice. This is from a different textbook. Okay, that's an example with a real inductor. Basically, you end up having two resistors in series. Okay? So the entire solution is in there. You can take a look at that.
Hey, Professor.
Yeah.
I actually do have a question kind of going back to that RLC circuit.
Okay.
So for the capacitor and the inductor, so if you were going to find the voltage drop between those 2 points across the capacitor and the inductor, if it was like, say, two resistors, you would like add both the values basically, right? But since they're 100 degrees or 180 degrees out of phase, you would subtract one from the other.
Yes.
Is that like the idea?
Yes.
So basically, instead of like, oh, because they're working in opposite directions. So it's kind of like having like a loop over a battery. You're going like the current's in the opposite direction. Is that kind of the idea?
Yes.
Okay.
Yeah, the current.
And
You're
so-
right. The currents
yeah.
are in opposite directions. That's why that circuit, that parallel circuit I showed you, when they were in resonance, the battery wasn't drawing any current, or the power supply wasn't drawing any current.
Because the loop is actually just the parallel loop. That's the only thing active.
Yes.
Okay.
Okay. So I do have. Oops. Let me go past this. I do want to talk about the transformer, but I'm going to hold off on that till lab. Okay? I'm going to hold off on that till lab. All right, so I've covered everything I wanted to cover in this chapter. And so I want to begin a new chapter, the last chapter in this unit. Well, normally it's the last chapter in this unit. Like I said, I'm going to split the exam so that exam 4 is just chapters 32 and 33.
So we've just finished covering all the exam content, or is this the last chapter for the exam?
We've just finished covering all the exam content. And
So this last chapter is the test 5, the exam 5?
Yeah, so this will be on test 5. This material and the material that I cover on relativity in the last. So we only have one more lecture this semester. Because we miss. Oops. Here. Because we miss next Friday. We only have one more lecture. And that kind of concerns me, but it is what it is, I guess. So that's why I decided to split the exam. Part of it is so I have enough material for the 5th exam, too. Okay. And usually from the chapter 34 material, I only put one problem. And most likely in my discussion here, I think I'm not going to talk about momentum and radiation pressure. I think I'm going to get to the point where I just describe the Poynting vector, and then I'm going to stop. And a lot of the material in this chapter, there's a lot of hand waving because the math is beyond the scope of this class. This material can be pretty hard. So I'm going to kind of, I will skip, I'm going to have to skip some things just for time. But anyway, the way we cover the material in an introductory course is very, we don't get into much depth. Okay. There's one problem I'll probably go through in some depth, but I'm not sure if I'll get to it today. Okay. All right. So I need to go back to Ampere's law. Before I go on, I need, and go through this chapter, I need to talk about Ampere's law again. Now, this topic sometimes in books is sometimes covered in this chapter and sometimes it isn't. So once I go through and re-discuss Ampere's law and make a correction to it, then we're in a position to actually write down all the equations that are used to describe the material in this course. So let's look at Ampere's law again. And I want to consider the following. Suppose I'm charging a capacitor. And I want to apply Ampere's law to a charging capacitor. So let me go up on the board. And let me reiterate Ampere's law for you. Because there's some details in it that are very important, that are often overlooked when you first learn it. So suppose I have a capacitor, suppose I have a capacitor. Let me spread these plates out more. And I'm charging the capacitor. Let's say it's charging as I talk about it, so it's charging slowly. There's a big resistor here that makes the RC time constant big. Okay, so it's charging as I talk about it. And I want to calculate the magnetic field due to the current in this wire, maybe over here at point A. And I want to calculate it right here in between the plates. And let's pretend that this is a very long wire. And this separation is not that big compared to the length of the wire. Obviously, you would know how to calculate the magnetic field here, right? So you would use Ampere's law. You'd say, okay, well, I'm going to make a loop. Of radius r. And Ampere's law says that the integral around a closed loop of B dot ds is mu naught times I enclosed in the loop. Whatever's penetrating the loop, right? So there's current that penetrates this loop, and we'll call it I sub c. And so this is just I sub c, right? So this is going to be easy. I'm going to say, okay, well, this is B times 2 pi r. All right, we've done this before. And we're done. What about over here? What if I want to find the field there? What do I do?
Don't you need the electric field between the plates?
Why are you saying that? I guess.
Because there's no actual current flowing. There's just a potential difference being created, right? With
Yeah,
electric
so
field.
what you said is very intuitive, that somehow the electric field's got to play a role here, right? Well, first of all, is the magnetic field going to be zero here?
It shouldn't, because it'll be perpendicular to the electric, right?
Well, I mean, yeah, you're right that the electric field is going to be perpendicular to the magnetic field, but I guess the question is, is there a magnetic field here? And then because we have a long wire, you would say yes, right? I mean, you can probably try to use the BO sub R law to calculate the magnetic field, because you have charges moving on these plates, right? These plates are getting charged. So those plates are getting charged. And so, yeah, you would say, okay, I know there's going to be a magnetic field here, but what if I draw my loop and what's I enclosed?
It's 0.
Yeah, I enclosed is 0. I know the magnetic field is not 0 over here. I'm quite sure of that. In fact, if I did an experiment, I would see that the magnetic field is not 0 there, so there's something wrong. There's actually something wrong with Ampere's law written this way. And the reason there's something wrong is because this only applies for the case where things are time independent. Okay. So what do we do? Well, in fact, let me make it even worse for you. Okay, let me make this problem even worse for you. Ampere's law says this has to be true for any surface I choose, any surface enclosed by the loop. In other words, whether I choose the surface that's in the plane of the loop or this surface, Ampere's law, it must hold. Okay. Whatever surface I choose to do the calculation, and normally we choose the loop that's in the surface that's in the plane of the loop. But there's nothing that says I can't choose this one. In fact, Ampere's law says that I can choose that one. This goes back to vector calculus, that this has to be true for any surface enclosed by the loop. Well, what if I choose this loop? I'm sorry, what if I choose this surface? What if my loop includes this surface? And not the plane. How much current goes through that surface? Forget about this surface. This is open. And just consider this guy. How much current goes through that guy? How much current penetrates this surface?
Oh, I sub C?
Remember, this is all open. Just imagine take a hat and put it sideways.
Then it's 0.
It's
right?
0, right? Same problem. We have this problem that this doesn't work in this particular case. Okay? So now what? I mean, in fact, if you consider the entire closed surface, you actually have a net flow of charge in or out of that closed surface, don't you? It's as if there's some source inside here, right? If you include the entire closed surface, there's actually a net amount of charge going in there per unit time. So, I'm sorry, go ahead.
The capacitor plate's the source, isn't it?
Yeah, the capacitor, you're right, is the source. So we got to account for that. Right? I mean, in this case, if I look at the everything that's inside here, There's actually a net charge flowing in here over the closed surface. In other words, if I took the integral of the current density over the closed surface, this is not zero. As opposed to if I did the following. If I had a continuous loop current, the same current goes in as goes out of that surface. That integral is zero. But in this case, it's as if there's some source coming inside. And so there's a flux of current going into there. There's a flux of charge. What kind of flux is related to charge? What kind of flux did we learn about that's related to charge? Going back there early in the semester, what does Gauss's law say? I mean, isn't the electric flux related to charge?
Yeah, I don't remember the equation.
Okay, but I mean, and you don't have to remember the equation, but the electric flux was related to the charge, and in the case of Gauss's law, the flux enclosed in the flux through a closed surface is equal to is related to the charge enclosed. So Maxwell, and Faraday knew about this problem too, but Maxwell was the person who came up with the solution. Maxwell said, you know, if the integral of V dot ds is equal to minus d phi sub b over dt, and nature is symmetric, why can we have this integral related to the time rate of change of the electric flux? And this was the answer to the question. This is how we came up with the solution to this problem. There's a term missing here. He said there's a term missing here that's related to the time rate of change of electric flux. And he said that the term that's missing here looks like this. This is the missing term. Remember, Gauss's law looked like this. So imagine doing this over an open surface. This is the flux through an open surface. And then multiplying this by epsilon naught. You can see the units of charge there. And so what he did was saying the integral of b dot ds is equal to mu naught times I, and I'm going to call it I sub c because this is called conduction current, plus epsilon naught d phi sub e over dt. And he called this term I sub d the displacement current. Not a good name, but okay, and so this solved the problem. So how does this solve the problem? I guess that's the question. How does adding that term solve the problem? So I guess we need to go through that. Okay. So Ampere's law, the correct version of Ampere's law is this. Okay. So it's the integral of B dot ds is mu naught times the conduction current plus the displacement current. But I still need to show you how this works. So this new form, though, of Ampere's law implies that both current and time-varying electric fields produce magnetic fields. This was a big deal. This is where Maxwell was able to put all his equations together. And from that, he actually derived some interesting stuff. So let's take a look at this displacement current. And in particular, I want to look at applying Ampere's law over this surface. Or, if I want to, I can apply it around this loop. Either way. So let me redraw, because I got a mess here. Let me draw my picture. And I'm doing a parallel plate capacitor just because of the fact that the field is easy to work with. The field's uniform. Let me draw this again. A lot of times people write I sub C here just because they call it the conduction current. Okay, the arrow of my picture is wrong. The arrow for the current. So let's say this is positively charged. This is negatively charged. Oh, never mind. Let me go with the picture. Never mind. The picture's okay. I have the current going this way in the picture. I don't know why I switched that around. So the electric field is directed, obviously, in the direction of the current. I'm sorry. So let's choose this surface that's in here. And it doesn't matter whether I choose something like this or I can start out here, choose a loop, and then draw that weird shape over here. It doesn't matter. Or I can do this too. That would be interesting too, right? So Faraday, Ampere's law says that the magnetic field is related by this equation. Suppose I just consider the surface that's in the plane of the loop. Consider surface in plane of loop. Okay? There is no I sub C, so this is 0. So I have the integral of b dot ds. This term is 0. Now, the electric field is uniform. What's the flux through this surface? What's the flux through this surface? No matter how big I make this ring, this loop, the flux is going to be E times A. Okay. We have a field here that's varying with time because the capacitor is charging up. So my integral of B dot ds is mu naught epsilon naught d over dt of E times A. Now the A is constant. Only the E varies with time. So let me go to the other board here and rewrite this. And of course, since I'm going to say the magnetic field is going to be in the radial direction, I'm going to write this as B times 2 pi r is equal to mu naught epsilon naught times A dE over dt. What is the electric field between two parallel plates? The electric field between two parallel plates is sigma over epsilon naught. What is sigma? Well, sigma is Q over A. The A's cancel. The epsilon naughts cancel. What's dq dt?
Current.
Current. And look at that. It works. Just 1 second. Okay? Does everybody see it? It works. Just adding this term works. So now I get consistency. I mean, if you think about it, if these wires long compared to the separation between the plates, it's not going to make a difference. You're going to get the same field there. What if I choose this surface instead? If I choose this surface instead, then this term is 0 because there is no electric field here. The electric field is between the plates is sigma over epsilon naught, but outside it's 0. And then you just get your old version of Ampere's law, the integral B dot S is just mu naught times I, and you get the same magnetic field. So you see how this works? This makes Ampere's law consistent whether the current is constant or not. And that displacement current guarantees continuity through the surface. Like I said before, if I just had surface like this and I had a current going in, whatever goes in goes out. The integral of J dot N dA here has to be 0. If it's not 0, there's got to be some source inside. And that's what guarantees continuity, that whatever goes in equals whatever comes out. Okay, so, but if there's a source in there, you got to take that into account. Now, the displacement current is not, it's weird because when this space here is a vacuum, there's really no charges moving in between here. But everything's due to the electric field. Now, when you have an insulator here, there is charge moving because of your polarizing charge. But in a vacuum, there is no charge here. So the electric field is doing everything, right? Right. That insight that was brought early in this lecture was great because you saw that the electric field had to play a role here. Okay, so we've already calculated the magnetic field between the plates. And what you see in these problems is what do you think this value is equal to in between here? I mean, as I evaluated the integral, as I evaluated this integral over this surface, what did this come out to be? All right, what was all this equal to?
That's just I sub c, right?
Yeah, that ended up being I sub c. So in that question right there, it says, what is the displacement current? And, I don't have to go through the whole problem because we already kind of went through it. That I sub c, the displacement current is I sub c. Okay. This thing is, well, in this region is equal to I sub c. Are we okay with that?
Yeah.
Okay. So I'm not going to go through any more details on this problem. Again, I am just in the interest of time.
Gauss's law states that the total electric flux through any closed surface.
Okay. These videos that I'm skipping because only the audio plays goes over the important equations we've covered this semester. So let's go over them real quick. So here's one of them, but let me start at the top. So, at the beginning of the semester, we learned Gauss's law. Right? So we have a Gauss's law equation for electric fields, and there's a Gauss's law equation for the magnetic field. And now we just learned the modified version of Ampere's law. You can also write it like this. And it's interesting when one is 0, the other one's not. Although there's cases you can think of where they're both non-zeros, but those problems are very hard. And then we have another equation, Faraday's law. These fundamental equations, which Maxwell looked at, form the basis of this course. There's really only one more equation that you need to be able to describe everything in this course, because we need a force equation. And so if you throw in the Lorentz force, everything you learn in this course basically comes from those equations. Okay?
Ampere's law asserts that the law...
Sorry. Well, let me go ahead. 1 second. Oh, those are our four equations: Gauss's law for magnetism, Ampere's law, and Faraday's law. Those are all four what are called Maxwell's equations. Okay. Again, they summarize most of E and M, but again, if you want to add forces to it, describe forces, you need the Lorentz force too. Okay. So, why are these important? Well, beside the fact that they really describe everything in this course. Maxwell took these equations and manipulated them. And from those equations, he was able to predict electromagnetic waves, because that was not understood at that time. In other words, light waves. Even though they knew about light, the theory of light wasn't really well developed then. I mean, some fundamental effects involving light were described using various models, but these equations, working with these equations will allow you to explain really all the phenomena involving light that was discovered up to that point. You didn't need to have very different models. This would do everything for you. So as he worked around with these equations, he was able to predict electromagnetic waves and their property. So if you solve the equations for particular, for various cases, you can show that if we define y hat as the direction of travel of the electromagnetic waves that are produced, then y dot E, the dot product of the unit vector that represents the direction of travel of the wave with the electric field, and y dot B, which represents the direction of magnetic field, is 0. It just says that the direction of travel of the wave is perpendicular to both the electric field and the magnetic field. And if you take the cross product of the direction of travel of the wave with the electric field, it's equal to some constant times b. That constant is called the speed of light. So he was able to come up with these equations. He used his equations to derive the laws of optics. He was also able to predict the speed at which these waves traveled. At that time, people had measured the speed of light, but no one had come with a theoretical expression for the speed of light. He came up with it. And notice what the speed of light is. It's the square root of epsilon naught times mu naught. If you take epsilon naught times mu naught and take the square root of 1 over epsilon naught u naught, you get 3 times 10 to the 8th meters per second. And this was verified by Hertz. In fact, quite a few of the predictions that Maxwell made with his equations were verified by experiments that were carried out by Hertz. One more thing he did with the equations is that he was able to predict that electromagnetic waves were produced when charges are accelerated. And you'll find out that there's two ways to produce electromagnetic waves. Either from transitions in atoms or molecules, or from accelerated charged particles. Those are the two sources of waves, electromagnetic waves. So, and here's where I am waving, because I'm not going to go through and solve Maxwell's equations because that's quite complicated. But I'm going to tell you something about the solutions to Maxwell's equations, especially for the case where the source of the electric and magnetic fields are really far away. And we're going to assume that the source oscillates sinusoidally. So the plane wave solutions to Maxwell's equations give you a wave that repeats just like the sine function or the cosine function. The distance between peaks in the wave, basically the distance between points where the wave has exactly the same physical behavior, is called the wavelength. The distance, or the time it takes for that wave to move from one peak to the next peak is called the period. If you take the wavelength over the period, that's the speed of light. 1 over the period is called the frequency. So the speed of light is f times lambda. This picture shows you the direction of oscillation of the electric field. It shows you the direction of oscillation of the magnetic field. And it shows you the direction of travel of the wave. All three of them form a right-handed coordinate system. If you take a cross product of the electric field vector with the magnetic field vector, the result is in the direction of travel of the wave. Notice that the electric field and the magnetic field are in phase, but the vectors are perpendicular to each other. That's important to understand. The electric field and magnetic fields are in phase, meaning their peaks occur at the same time, their zeros occur at the same time, but the direction of oscillations are perpendicular to each other. Now, you can solve Maxwell's equations for different cases. For the case where I is 0 and Q is 0, in other words, the sources are really far away, you can manipulate Maxwell's equations to get the two equations that you see at the bottom. Those are in one dimension, okay? A three-dimensional version is much more complicated. A three-dimensional version will have the second derivative of e with respect to y squared and the second derivative of e with respect to z squared. Same thing for the magnetic field. And these are they're not called differential equations, but they're called partial differential equations because of the number of variables that are involved. And the solutions to them are not easy to obtain. But we can always just talk about the solutions. The solutions generally look like that form, where the electric field is some function of the position vector plus or minus the speed of light times time. Where the plus sign, pay attention to this, the plus sign represents a wave that's going in the negative x direction, and the minus sign represents a wave traveling in the positive x direction. That's important to understand. And one of the simplest solutions to the wave equation involves sines and cosines. Okay, I think I'm going to stop here. And then I will continue either. Well, I will continue the next time you meet. Either not the lab. I probably won't continue this in the lab on Monday, but I'll probably continue this in the following lab on Monday. Okay, so I'm not going to see you guys for a while. So have a good Thanksgiving break.
You too.
All right.